Uh, Now we focus on module 4.4, which is molecular shapes. And molecular shapes rely on the correct Lewis structure. So I'll repeat, the molecular shape relies on the correct Lewis structure. So if we have the correct Lewis structure, we always focus on the central atom. The central atom. So for this example, methane, CH4, we have 4 electron pairs as far away from each other as possible. And this gives us a tetrahedral rearrangement. So if we look at the central atom, it has 4 groups, one to the left, top, right, and bottom. And there are no lone pairs on the carbon. This gives us a tetrahedral shape, and we'll talk about a few other shapes in the next slides. Lone pairs, if we what we mentioned in the Lewis structure section, lone pairs are the ones that are not bonded. They are unbound. So in this case, for ammonia, which is NH3, we have here one lone pair. We have one group to the left, one below, one to the right, and we have one lone pair. So when you have 3 groups and one lone pair, we call this a trigonal pyramid, a 3-sided pyramid. And why is this? Why is there a bend? It's because of this lone pair. We know that the bond is composed of 2 electrons, and when a lone pair interacts with a bond which has electrons, we know that electrons which are negatively charged don't like each other. So they repel each other. So they want to space apart from each other as much as possible. Hence, they make this trigonal pyramid shape. So we've talked about tetrahedral, and this one is trigonal pyramid. The next one is for water, and this is the correct Lewis structure for water, which has 2 bonds to the left and right, or 2 groups, left and the right, and we have 2 lone pairs. And when we rearrange everything, where we have everything has the most space as possible, again we have repulsion between the lone pairs and the bond, the lone pairs and the bond. This makes a bent shape. A bent shape is composed of 2 groups and 2 lone pairs. And again, we always focus on the central atom. 2 groups connect to the central atom and 2 lone pairs on the central atom. If we did not have these lone pairs on water, so if you drew the Lewis structure and there was no lone pairs on your structure, it would not be bent. It would be something called linear, which is similar to CO2, which we'll talk about in a second. But water, and as you've seen in textbooks, is a bent molecule. And why is it bent? It's because of these lone pairs. As I just said, linear, where if we focus on the central atom, again, this is the correct Lewis structure of CO2. Carbon in the middle, we have double bond to the left, double bond to the right. We treat double bonds, single bonds, and triple bonds equally in this case. We have one group on the right, one group on the left, and we have no lone pairs on the central atom. We do have lone pairs on the oxygens, but again, when we're talking about shape, we always focus on the central atom. So when there's 2 groups and no lone pairs, the shape is linear, and it's 180 degrees straight line angle. So we focus on chemical compounds that are relevant to the environment. So we focused on CO2, water. So here we have CO2, which is linear, straight line. We have bent ozone. Bent can also be 2 groups and 1 lone pair. Bent can also be 2 groups and 2 lone pairs. And you can see by the molecule drawn, it is in a bent shape. So remember, O3 is ozone. It is a bent molecule, and water is also a bent molecule. The common shapes that we should be familiar with: linear, example is CO2, bent H2O. We also have bent with O3, which is two groups and one lone pair, not in this table. So I'll just draw that now. We have O3, which is also bent, and it has two groups and one lone pair. This is also bent. We have here trigonal planar, which is made up of three groups and no lone pairs. The ammonia, NH3, which is three groups and one lone pair, and that causes the trigonal pyramid formation. If I go back, trigonal planar is just a triangle, and all these three are touching the paper. It's flat. And tetrahedral was the first example where we have four groups and no lone pairs. Again, we have to have the correct Lewis structure first, and then we focus on the central atom. So let's try a couple. I'll draw the Lewis structure for you just to make it more simple. You can pause and you can tell me the shape. I'll give you a clue. Starts with a T. Tetrahedral, if you're listening. If you're just watching. And in this case, we also focus on the central atom. I forgot to draw the lone pairs for the Lewis structure. Not important in this case because we focus on the central atom, but this one is tetrahedral as well. The hydrogen sulfide, SHH. This is bent because it has two groups and two lone pairs. And next they're asking you to draw the shape, and I'll give you a clue. This one starts with B. And this one starts with, well, let me just draw the Lewis structure for you. This one will start with a T, trigonal, and we'll just leave it at that. Let you solve the end. It's either trigonal planar or trigonal pyramid. So molecules behave differently when they interact with, for instance, UV radiation. Bonds can be broken. If they're interacting with IR, infrared, they can vibrate. And when you're dealing with microwave, which are longer wavelengths and less energy, they can rotate. And the next slide is we'll focus on this IR with CO2. So we just said with IR, it can vibrate. And here we have examples of, again, the C is in gray ball and O is the red balls. We can have different types of vibrations. We can have a symmetric one where the left side goes left and the right oxygen goes right, but they cancel each other out. And this is upon receiving IR radiation. So if there's no net movement or net dipole, there is no absorption. So for A, there's no net charge of electron distribution, no IR absorption. However, for B, we have an asymmetric vibration where the O and the carbon, they cancel each other out, but you still have the oxygen on the right pulling. So overall, there is a net change in dipole. For the carbon, for C, we have something called a bending. You can see the carbon goes down, the two oxygens go up. This causes a bend. So when you have a dipole change, a dipole meaning the carbon is more positive and the oxygen is more negative, there's a dipole change. And here we also have bending for D, where the carbon goes towards us and the oxygen goes away, giving a net dipole change. So I think what we have to get from this is if there is a net change in dipole, we have IR absorption. We'll stop there till the final module.